And welcome to this first step in the RISC-V low-level JavaScript hardware FPGA CPU extravaganza. Now, we're going to not begin with the hardware CPU and the FPGA stuff and gateware TS for now. What we're actually going to do is we're going to build a RISC-V emulator. And there's a couple of reasons that I want to start out that way instead of diving straight into the hardware. Actually, there's many reasons that is a sort of a good idea, but the biggest ones are that, you know, hardware is hard, and it's quite kind of unforgiving in debugging terms. So especially FPGAs, they're sort of notoriously difficult. When you run into bugs, you're just sort of left scratching your head. And in order to, well, so hardware is hard in general, and also building CPUs is hard. So sort of combining those two complexities together and sort of trying to do that all at once is kind of, yeah, it's a recipe for disaster in that way. And there are, of course, ways around that, and there are things that we're going to do when we actually do get to the FPGA build that are really going to help that out, including things like simulation and doing almost like TDD style simulation as well, which is something that I've set up with gateware TS already. Now, another one of the reasons is I think it's actually just useful for communicating in the videos, so everyone is on the same page that's watching, and we can all, get something out of it. Kind of what RISC-V is, and what we're talking about, and what the instruction set is, and kind of like what all of the bit kind of manipulations we're going to do are, and also to explore the concept of pipelining, which isn't something that we've ever looked at on this channel before. So we've been building a 16-bit virtual machine for a long time. RISC-V is going to be a 32-bit machine, so we're already stepping up, architecture there. But what we didn't have in the LRGS VM, and indeed often in virtual machines, you don't really do this anyway, but is the concept of pipelining. And pipelining, well, I'm going to get into it, of course. Maybe I'll just open this up already. Pipelining is the idea that that you can have a single-threaded CPU, so one core, but you can still kind of execute multiple instructions in parallel. And the way you do this is you split your CPU design up into little modules that are sequential, but can also run in parallel with each other. And this is called the pipeline. And this is kind of very common now. I mean, actually, this is the only way that CPUs are built now. I mean, in the days of yore, CPUs were built unpipelined, but that is just not the case anymore. And even the simplest of CPUs will have pipelines. And in modern CPUs, and like serious CPUs like Intel are producing, the pipelines get really long. This is going to be a pretty short pipeline. It's not the shortest pipeline you can make, but it's going to be pretty short. And basically it consists of multiple stages. And so what we're going to have in the CPU is it's going to fetch an instruction on one clock cycle, and then it's going to communicate with the next stage on the next clock cycle. It's going to pass on its results. It passes on its result, and at the same time it's passed on its result, it can begin fetching the next instruction. And then you can see that after the instruction fetch, there is a decode stage. And what that does is that looks at the instruction that's just been given, it kind of pulls out all the relevant information from it. I'm sorry if you can hear the sound of this boiler in the background. It sort of just decided to turn on. So the decode is pulling stuff out of the instruction, and we'll take a little look into the instructions and how they're encoded, because RISC-V is a really clever encoding, and there's a lot of information packed into just each instruction. So once we grab some of that information out, we can pass all that stuff to the next stage, and we're ready to pull in like the next instruction that the instruction fetch stage has given to us. So after the decode, we get into the execute stage. In execute, that's pretty much where like the arithmetic and stuff like that is going to happen. So like all of your, you know, additions and your ands and your ors and your shifts and all of that kind of stuff. And in more advanced CPUs, things like multiply and divide, all of that kind of stuff is going to start happening in that execute stage. As well as some other things. Of course, you don't only have arithmetic instructions and these kind of things, you also have things like branching, and you have loads and stores. And so you can think like different parts of these different instructions, they're going to happen in different stages. So then after that, we've got a memory access stage. So some instructions, they need to access memory. And what we'll see in RISC-V is that you wouldn't ever have like an add instruction that's also going to access memory. Like that doesn't happen. So, you know, you can sort of rely on the fact that these pipeline stages can sort of run independently. And eventually, so we can read and write to memory in the memory access stage, and then eventually we get to the write back stage, and that's where we might be putting the results of something back into a register. And that's it. And then basically, I'll show another diagram, sort of a better diagram that you can see. This is the classic RISC pipeline Wikipedia article. So RISC-V is a kind of architecture, but like it's not the only RISC architecture, and RISC is just a general idea that a bunch of I mean, it started off in academia, and a bunch of academics figured out sort of different approaches and all learned from each other. And so there are various famous RISC architectures. So RISC-V is just a very recent thing, and we're going to, you know, of course we can talk about what RISC-V is and why it's innovative for the open source aspects, but it's also just building on a lot of stuff that's come before, like MIPS and Spark and Motorola 88,000, although I don't really know anything about that architecture. Yeah, and a couple of others. And yeah, so this is actually the diagram I wanted to show here. So this is the pipeline. This is exactly the same pipeline I have in this other diagram. So what we've got here on the sort of horizontal axis is time, as we're moving on in time, and in the y-axis going downwards, we're sort of like parallelizing or moving through different instructions. So you can see at the very first instant of time, we're just fetching an instruction. But on the next sort of clock cycle, well, now we're decoding the result of that first instruction, but also we're fetching the next instruction. And then, of course, on the next clock cycle, we're executing what we got from the first decode stage. But we're also decoding again what we got from the second round of instruction fetch. And what you can see is that at some stage, you can have 5 instructions running in the pipeline at a time, because there are 5 instruction stages. There are 5 pipeline stages. And so you can have like a 5-level parallelism here on a single threaded CPU, which is pretty cool. And it's not perfect, of course. You can't, like, there are exceptions to this, of course. Like, you can imagine that, like, you start running an instruction, you decode it, and you might like have an instruction which is like add 2 registers, add A and B, and put a result in C. These aren't real register names, but for the sake of it. And what you might imagine is that the next instruction somehow is going to depend on C, so maybe it does another arithmetic operation on C. You might have like add C to D and put it in E or whatever. The problem is going to be that if you just run the pipeline naively, and what is implicit here, and I haven't said explicitly, is that between each of these stages, there's a sort of like a register, if you will, which is holding the value and passing it to the next stage. So that value is being passed along, and so by the time we get to sort of like executing, and then we're eventually going to write back, you can see that if we're writing the result of our add operation back here, we've actually already executed the next instruction ahead. So we've computed what the result of the register is going to be. That's going to eventually get written back, and so that's going to be wrong. And so what you need to do if you're kind of running this kind of pipeline is you need to have a mechanism in which you can sort of communicate backwards and or forwards or something. You need a communication mechanism in which you can check if you have dependencies between stages. And of course, the longer your pipelines are and the more interactions you have, the more difficult that can be. But that is the general idea. And yeah, we're going to talk about how we're going to get around some of this. And I don't want to talk too theoretically for too long because I've already been talking for 10 minutes. So I actually really want to get into the code here. I don't want to make this video too long, but I do also want to make some ground in the emulator. So one of the most important things to understand right now, and also to understand what we're going to do with the CPU when we build it in hardware to begin with, is we are not going to implement parallel pipelines. So we're gonna implement a pipeline. We're going to implement these stages, and we're going to move the thing forward. But we're not going to parallelize it in the beginning. So it's going to be a really naive pipeline where every clock cycle you simply go through, but all the other instruction stages are blocked until we've gotten the instruction stage from fetch up into write back. So that's a really dumb processor design. That is like, you know, one of the worst things you could do, because you're not even going to say, okay, I'm going to have a single instruction and I'm just going to try and, you know, optimize for the idea that I'm executing one instruction at a time. So if you think about it like that, you don't necessarily need to make 5 stages because you could. That means you execute 5 clock cycles per instruction, which is not great. Sort of trivia wise, there is the idea that the 5-stage classic RISC pipeline is supposedly supposed to have like a 1 clock cycle length of each pipeline stage. So the idea is that you would also have a 5 clock cycle instruction. So you would have this sort of latency for each instruction, but you're actually, after your initial sort of bootstrapping stage, you're actually executing 1 instruction per clock cycle. So it actually starts to become a really fast design in that way, in the best case scenario, where you're not branching. Branching is the other case, of course, where you have dependencies between stages, because when you want to do a branch, that means you want to jump conditionally based on some stuff. You don't know whether that condition is going to be true or false until you actually come to evaluate it. So what you can be doing is, like, you get a branch instruction, you start moving it through the pipeline, but you're beginning to execute other instructions before you actually get to that point. So that is where interesting things like branch prediction comes into play. And that is like a piece of hardware that will try to work out like where it should get the next instructions for while it's like running in the pipeline. Because if you manage to guess correctly, then you don't need to undo any of your work. But if you guess incorrectly, or you simply don't implement branch prediction and you sort of just naively assume branches won't be taken or they will be taken, then you're only going to be right about 50% of the time. And in those instances where you're wrong, you're just going to have to obliterate everything in the previous stages. So as soon as you know that branch is taken or not taken, and you know the work you've done is wrong, you need to just throw away all the stuff because you can't use it anymore. And so there you basically stall the processor in those parts until it can get itself back on track with new instructions. So interesting stuff. We're not going to do any branch prediction stuff in the beginning. So what I'm going for basically is the simplest possible setup. But I want to build the pipeline now because I do actually want to have parallel pipelining eventually. But I just want to get to that point where we have a processor, a hardware processor that is like executing proper RISC-V programs that come out of like real RISC-V toolchains. I want to get to that point first and be able to somehow communicate outward from the processor. So be it whatever method comes up. I'm not exactly sure what we'll do yet. We'll definitely have some sort of serial communication, but not exactly sure if we're going to end up going more sophisticated than that. We'll see how this turns out. I want to get to that point before I start like going even further, because there are many ways you can go further. You can think about caching, you can think about things like branch prediction where you can go really far. Yeah. So we're going for the simplest possible solution. So today, what I actually want to do is I want to get to the point where the emulator, we've set it up There's the idea of a memory architecture, so that there is like, we're going to use memory mapped I/O just like we did in LLJS VM. So if we write or read to certain memory locations, we can actually be communicating with different kinds of devices. So we could be communicating with ROM devices at some moment, we can be communicating with RAM, we can be communicating with like hardware registers. So writing to certain memory values will be controlling parts of the hardware. And then things like UART serial communication, we'll have registers for that. We'll probably have registers for, in the beginning, for really simple stuff like LEDs on the board. It's just so that if we write to certain registers or certain memory locations, we can just change LEDs on the board and see things happening. Yeah, I also don't know which hardware I'm going to use yet. I have a couple of FPGAs and FPGA boards here, but I don't have anything with like DDR memory attached to it, or like any kind of form of like memory greater than a couple of megabytes. And I would kind of like to have that. I would like to be able to have enough memory to play with that it's not like going to be so ridiculously constrained that it's not fun. So I'm looking at a few different FPGA boards and solutions, and things there that, you know, I don't particularly want to write some really, really specific hardware related stuff. Like I don't really want to write a memory controller from scratch because it's really complicated and difficult, and there are so many edge cases. And if you get sort of FPGAs that aren't, well, that are from some of the bigger manufacturers, they often have this kind of stuff pre-built, so you can just sort of drop it into your project. So that's probably what I'm going to do. We're not doing the hardware stuff today, so let's forget that for now. Let's get into the emulator. So I've got one more picture to show, and that is like of this sort of like memory layout, you know, way that the system is going to, the CPU is going to communicate with memory and how that's going to go out. So what I'm thinking right now is that we're going to have, you know, we're going to have some sort of system interface. So the CPU is out here, imagine, and there's some sort of way of sending out an address. The address is 32 bits wide. Everything is 32 bits wide on this architecture. Although stuff that comes out of memory might actually end up being like bytes, and we have to do some work to turn it into 32-bit integers, but that's for now we'll just imagine everything is 32-bit integers. And yeah, so we've got an address line, we've got data that can go in and out, and we've got some sort of read-write line that says if we're reading or writing. Basically what we're doing is we're talking to this interface that is going to do memory mapping for us, and what that's going to do is go out to stuff like a ROM. It's going to go out to RAM. It's going to go out to, you know, the universal asynchronous receive transmit. I think that's what that says. That's serial communication. It's basically just, yeah, printing and sending stuff backwards and forwards, bytes, over a really simple protocol. Something you would use in Arduino, for example. And then, yeah, LEDs or something like that, or switches or whatever is going to be on this board. There'll be a bunch of stuff, and so this will actually be like a bunch of hardware registers to talk to, you know, onboard stuff for configuration and things like that. So yeah, we're going to have to build this. That's going to be pretty important. I'm thinking to actually have like segmentation between like program code and running memory. Not for any sort of security purposes or anything, but I just think it can simplify life a little bit in that way, if you just know that your code isn't going to change once you put it in memory. I think it will also help for debugging purposes, because what you really don't want that to happen while you're just not expecting it to. Yeah, so we're going to do this, and we're going to start setting up something for this. And I don't know how far we can get. I've already wasted 20 minutes just blabbering on. But yeah, I would like to get this. I would like to be able to just execute a single instruction, like an add instruction. Maybe not all the way through, but I would like to get to the point where we can, you know, add some registers together, and so maybe implementing these 3 pipeline stages, it might be a bit of a stretch, but let's go. Let's actually start. All right, so I'm here. I've got an empty project, right? I've just installed TypeScript because, you know, the hardware is going to be written in TypeScript, so let's write the emulator in TypeScript as well. There's nothing else installed, just TypeScript, just TS Node for executing the TypeScript stuff to make it easier. And yeah, let's get started. So we're going to have a class. I'm going to use classes and stuff. I'm not doing some huge object-oriented thing, but I just think it's kind of useful in many ways to just put these things together in classes, because this is gonna mirror pretty closely how the hardware ends up looking in many ways. I mean, it's not going to go all the way to the detail level that the hardware will, but this is going to get really, really like close. And what I would like in the end is that we can copy paste tons of stuff out of this into the hardware code. That we do all the hard work here, working out bits and like slicing up the instructions and all that kind of stuff. Yeah, so we're going to have like I'm going to call it RVI32 system. That's RISC-V integer 32-bit. And we'll refer to this manual here. I had it open in the beginning, but basically, you know, RISC-V is a sort of modular architecture. It's got a base set, so that's the 32-bit instructions. And I'll actually just really quickly show you the instructions that we have to implement. It's these. And I can just barely not fit this on the page. This is it. This is all we need to implement. And tons of this is just the same. So like everything from here, this instruction onwards, selecting stuff in PDFs, man. These are all the arithmetic instructions. So that's just the ALU. You can see that that's such a huge chunk, and that is like all really simple stuff. Like this is loads and stores, so you know, pulling stuff out of memory and putting it back. This is all doing jumps and branching, and so conditional execution. This is more sort of loading stuff into registers actually, but like specific for really specific reasons. We'll get into that. These we're gonna implement as no ops, because we're definitely not implementing a sophisticated architecture that's going to have fencing. These are like to do with interrupts and debugging. We'll get to those eventually. And these are like system control register stuff, which we'll get to as well, like RISC-V mandates that we have to build in some like timers and things like that into the CPU, because that's useful. And these instructions just allow you to manipulate those. What these instructions like RISC-V is a modular architecture, so this is the base. But there are then modules that you can add on. So you can add on this. This is the 64-bit edition, so you can add these instructions and you can operate on a 64-bit architecture. This is the M extension, which adds multiply and divide and remainder modulus kind of stuff. Yeah, and you've got a couple of different extensions. We're going to focus only on the base instruction set, of course, going for simplicity. But yeah, you can see we don't have to do too much, and you can see that there is a huge amount of pattern in here. Like you see the columns. This whole thing represents like the 32 bits of an instruction, and these are the different parts, the different bits and the meaning they have. And you can see like RS1 is like dealing like with a source register. So it's like you've got a register which is going to have some influence on this instruction. You can see it's always in the same place. That's so nice. Like it makes the decoding instructions like super easy because it's just always there. These 3 bits which are in the middle, they may or may not have some sort of other decoding effect. So like they encode a more specific piece of information about a single opcode. So this is like, you know, in the ALU, for instance, this selects which kind of operation you're going to do. Like every arithmetic operation is the same instruction, but this selects the specific one. You can see that the RD, that's the destination register, that's always in the same place. And sometimes we have a second source register as well, and that is also in the same place. And then we have things like immediates. An immediate is, I think I talked about this in LJS, we call it a literal value there, but an immediate is just something that's immediately available. It's the immediate literal value that you have. So that's how they call it in this processor architecture. So yeah, that's it. That's what we're going to implement. We're not going to implement all of this today, nowhere near. That's why we're implementing an RVI32 system. So we don't really even need this class for now. Let's actually start with the memory. So I'm gonna call it the system interface. I don't know if that's a good name, and I might change it. But so we're gonna export class system interface, and this is pretty simple, right? We're gonna have a read method, and we're gonna have a write method. Those are the two most important things. Read is going to take an address, which is a number, and it's going to return a number. So return 0 for now. And write is going to take an address, which is a number, and it's going to take a value, which is also a number, and it's going to return nothing. We don't care. So for now, we're going to do that. And then we're going to have memory map devices. So I'm going to create an interface, export, and I'm going to call it MMIO device. Well, keyboard shortcuts getting me. And we're going to have a read method, right, which is going to take the same stuff, and that's going to return a number. And we're going to have a, oh, it's not like this in the interface. Then we're going to have a write, we're just going to have that value number. We're actually not going to return anything from that. If this is your first time seeing TypeScript, by the way, don't let this scare you. All we're doing here is like making it clear what the stuff that comes in and out of the function is going to be. Like, it's nothing too scary here. And an interface, so here we got a class, it's like this concrete thing with methods and stuff. An interface is like the idea of describing a shape of anything. Could be an object, could be a class, whatever. And you can say like your function, for example, takes an interface instead of like a specific class. And anything that fits that interface is allowed in. So what we can say is that we can implement these devices in any way that we want. As long as they have a read method and a write method that conforms, it's good. Weirdly enough, I'm actually going to say that the system interface implements MMIO device, which is kind of weird, right? Because it doesn't, but it does as well, right? It implements the read-write interface. So I'm just making that clear. All right, and what I want to have, right, is for now I want to have program ROM, I want to have some RAM, and that's it. We don't really need to have anything else for now. So, do we need anything specific? Yeah, okay. Let's have a folder called System Interface. I'm just playing this completely by ear now, so I'm probably going to change a lot of this around. So we've put that just as the index of this folder, and then I'm going to make a file called ROM, where I'm going to export a class ROM device, which implements MMIO device, and that means we need to implement these two methods. TypeScript tells us what we need to implement, which is really handy, right? So we need to read from an address, which is a number. Now return 0. And we need to write to an address, which is a number. And we don't need to return anything. So now this is legit. This is a device. And what I'm going to do in here is I'm going to... how am I going to do this? I'm wondering if I'm going to make the system interface like the owner of the ROM, or if I'm going to put that inside the RVI32 class. And I think I'm going to do that because I think it's sort of like It doesn't really belong to the interface. The interface is just there to mediate. So for the idea of loading up the ROM with stuff, I think I'm going to have that go somewhere else. So what I'm going to do is I'm going to say that we're going to have a ROM on the interface. I guess I'll do it like this, private ROM. I'll make it private here. I'll say that this is a ROM device. And we're going to do this via a constructor. I'm going to pass in the ROM here. So it will be... So the ROM is going to come from the system, the RVI32. Okay, another thing that we want to have is like an enum, which is going to describe the memory map, kind of. So yeah, so in this diagram where I showed the system interface, I used some numbers here. So I've got program ROM starting at hex 1, many numbers. Andreas Kling always calls this like a fragillion, so like 1 fragillion. RAM is going to be at 2 fragillion. You are at 4 fragillion. We're just going to forget these two for now. So we're just going to put, I'm going to put the thing there. And what you can see is that I'm just using that top, the most significant nibble to just like be the selector of which we're gonna, of which thing we're gonna address. And you can see that's wasteful because there's probably only going to be a couple of megabytes of program RAM and a couple of megabytes of program ROM. And I mean, if there's LEDs, we're definitely not going to use a whole fragillion for LEDs. So yeah, this is a bit wasteful, but this is a really easy way, especially in hardware, to decode this, because we just have to look at those top 4 bits. We could actually just like have a choice of 16 things and choose from those. So I'm going to do the same thing there. I'm going to say that program ROM, I'm actually going to do it like this. Program ROM start is going to be 1, 2, 3, 4, and then it ends. Well, it's going to end at like the end of this one range. So we'll say 1, 2, 3, 1, 2, 3, 4. So that's going to be program ROM, and then we're going to have RAM start, and that's going to be at 2, 4, and RAM end. It's not, I mean, it's actually not going to take up all this space, but this is just sort of defining its range. And I'm actually not even going to end up using these, right? But, oh, maybe I am. So when we're going to decode this, like, let's actually build the ROM first. So export const ROM size. Just want to define how big the ROM is going to be, and I think we can for now say it's going to be, so that's going to be like 1 kilobyte, and then we're going to have, what's that, like a megabyte. Let's just call that a megabyte for now. Yeah, so what we can do, right, is we can say that internally we're going to have something that we just call our ROM, and that is going to be a new uint32 array, and the size of this array is going to be ROM size, but we actually need to divide this by, because that's like a size in bytes, but we're defining the number of elements in a U32 array here, so we need to divide this by 4 because there's 4 bytes per U32 element. So let's divide that by 4. Or, you know, we could do the, no, let's not do that. Let's just do this by 4. So now we have this many elements. And when we do a read, right, we're going to say, there is this whole concept of alignment. I know I'm talking about so many different things in this video, and I hope it's like, if you have any questions, you know, just leave them in the comments and I'll elaborate on things in the coming videos. But we have this concept of alignment. So you can kind of see it here. If I was trying to read from address 0 of the ROM, so this 1 Fragilian address, right? I'll put it down on screen as well, right? In this case, 1 da, 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 da. If this was the address I was trying to read from, that's fine, because that is just going to, all I have to do is take that number, well, I need to minus this whole number from it as well. But yeah, you can imagine we're using this number to select, right? So what we're going to end up kind of, by the time it ends up in the ROM, we're going to get rid of that first number. And then we've actually only got, we can only address bytes. So we can only address these groups of 4 bytes because you can only pull a U32 out of this. So I can't ask for the second, like a U32 from like offset by 1 from the first, because that would sort of be 3 bytes from the first and the first byte from the next one. So you can't do that either. So that means we can knock off these first bits as well. So like we can knock off like 2 bits from the bottom of this address, which we can't do here because we're looking at hex and you can't isolate 2 bits, but we're ignoring 2 of those bits now. And then of course you've got to account for the fact that for now I'm going to have to solve this problem in like 1 minute anyway, but for now what I'm going to say is that the address that comes into this ROM device method is going to be an address that understands that it needs to be aligned to the 32-bit boundary, and it's going to, well, we'll make sure that we index this ourselves. So I'm assuming address is like going to be 0 coming in, like it's going to have been sort of taken care of by that point. So what I want to do is just this.rom, and then the thing we're pulling out of ROM here, it's going to be the address, but then we also only care about like 1 megabytes worth of this address. So like it could be in range, right? And it can be aligned, but it could still be bigger than 1 megabyte. So right, if we've got a megabyte, 1024 times 1024 in hexadecimal, that is of course this number, which is a little bit less than the 1, 2, 3, 4. So yeah, we could drop off these 2 zeros anyway. So we can just shift it down by 2. That's enough, right? What I'm getting at is that we only have to look at, we can just knock these 2 zeros off for now. But it would be better to like do this in relation to the ROM size instead. So if we wanted to make a mask now, so I'm sorry, I'm really not talking this out loud as I should be. So what I want to do here is I want to say that whatever they put into the address, we're going to make it valid by like, sort of like if they ask for something off the end, and by they I mean me, you know, if I end up asking for something that goes off the end of like the 1 megabyte boundary, if I ask for like something 4 megabytes in, what I want that to do is just sort of loop back and end up being in the beginning. And we can do that with a mask. So what we do is we take the ROM size, which is this, and if you just take away, in this case it's going to work out perfectly. If we take away 1 from this, what you get is a mask. This FF, is that 5 Fs? Yes, there's 5 Fs. So we have 5 Fs. That's going to isolate just the like that amount of the address, and then anything that goes beyond that is just going to sort of loop back according to that. I hope that's clear. So yeah, so what we're going to do is we're just going to, in this case, this won't always work. If we had like 4 megabytes, well, actually, I guess if you had like 4 of these, right? then you took one away, yeah, you'd end up with 3FF, and that would also be a valid mask. So I think within reason this would work, so let's do it like that. What we're going to do is we're going to take, we're going to AND it with just ROM size -1. And I think that should work. I mean, something might be wrong with that, but we'll see. And I'm saying we've dealt with alignment by this point. I think we need to take a value in when we write. So in this case, we're going to write a value to that. Cool. That should be all we need to do here. I hope that's right. And the other thing we want to do is to have a load method. And I guess here what we'll do is take a byte array. Or we could just take a uint32 as well, because we're also going to assume that when we load program ROM, that I mean, we might want to be like mixing data in here as well, like putting tables and stuff like that. Or if this becomes like anything crazy like a game console, which it could, we might also want to put things like game assets in here as well. I don't know, this is like a completely non-decision now, but I'm just going to say for now that this also takes a U32 array. So we're going to load up some data into this, because we need to get data into it. You know, it's a ROM, so it's not supposed to be loadable, but it's going to be loadable from like from like the how do you call that? Like the instrumentation point of view. I'm going to say that's a U32 array as well. And this is kind of like a weird way of doing it maybe, but what I'm going to do is I'm going to loop over the whole ROM size. I'm just thinking, I think this is wrong now, because I should be first dividing ROM size by 4 here. In fact, I'm going to end up dividing ROM size by 4 everywhere. Let's do it for now. Separate it later. Anyway, what I want to do is I want to go through each element of the thing, and what I'm going to actually say is when we load stuff in, like if data, well, if I is greater than or equal to data.length, then I want to say that ROM at I is going to be, or this.rom is going to be FF. Like, I just want to put, yeah, just all F's there in the case that there's no value that we're loading in. Like, we load a smaller than 1 megabyte in, we're just going to put FFs there. And, you know, I could easily make sure that doesn't happen when we build binaries, but otherwise this.I is going to equal data.I. I guess there's no real reason for doing that, but it's just kind of like, I guess, if we ever get to a point where, like, something's going wrong and we look into the program wrong, we just see that everything there is Fs, then we know that, like, the problem is there that something went either wrong with loading, or it can be a nice clue at the least. Okay, so that's ROM. RAM is going to be, I guess, a little bit easier, but pretty much the same. I think every instance of the word ROM here. Still also going to take the... Yeah, let's just replace it with RAM. And let's say RAM size is going to be 4 megabytes for the sake of it. It's easier to have more RAM than ROM, I guess. Well, actually, it's probably cheap to have more ROM. I don't actually know about that. We don't really need a load method for the RAM, because the RAM is going to be like, if anything, we should have like a randomize method, and that would like, you know, just put a load of random crap in the RAM in the beginning, because it would be really that is what it's going to be like on the hardware. The other thing that I've done is, obviously you can't actually write ROM, so we don't need this. This is actually just do nothing. You can't write to ROM. So we need to have a method there, but we're just going to ignore any writes that come in. RAM, we write to RAM, that's all good. So I guess we'll take in a RAM device here as well. Although the interface could also be like the owner of the RAM, because it's not like we're going to initialize it with anything. It's kind of all going to happen from the program side. So maybe just for simplicity now, I'm also going to make the RAM. You know what, I'm not going to do it. I am going to pass it in just for the debugging stuff. I think it will make debugging easier. So make that RAM. RAM. Cool. All right, and then when we read, what we're going to be doing is like looking at the address at this point. So what we want to do is take the address and say, hey, if we AND this with 0, 1, 2, 4, if we AND this with this number, and actually let's use the memory map here because we've got it. Memory map dot program start. And if that actually ends up equaling the program start, then like that's what we've selected, and we're going to direct our read into it. And when we do that, I'm going to get rid of that first thing, and I'm going to align this to. Yeah, then I'm going to align it. So this is how we're going to do it. We're going to say this.rom.read, and then we're going to take our address. And the first thing we want to do is align it. And I'm really not sure if I've made this concept clear or not, but let's just try and draw, like, I feel I'll go into this and we'll draw a diagram. So this is our memory, right? This is our, thinking of it as 32 bits. So each of these is going to be a byte. This is 1 byte, this is 2 bytes, this is 3 bytes, and this is 4 bytes. And together, 4 bytes form like one 32-bit number, like one 32-bit cell. So what you can imagine, right, is that we're going to have something like this. This is just a reflection, right? Because stuff is all bytes in the end, or it's actually all just bits, but this is our memory. All right, now, so address-wise, we're actually sort of talking about bytes because we can point, you know, we have a byte-based address. So what we're saying really is that it's valid to read like from this point and ask for a 32-bit number because it's aligned, right? We're like, if we read from here, we can read 4 bytes and we got one 32-bit number. Same then if we read from here, because it's another one. So this is going to be address 0. This is going to be address 3. Is that right? No, it's not. It's going to be address 4, right? 1, 2, 3, 4. And this is going to be address 8, and this is going to be address 12, which would actually be, what is that in, so it's A, B, C, it would be C, in hex. I'm not so fast with hex in my head that, which is kind of stupid because I've done, like, I've stared so much at it now and I still haven't drilled into my head this, like, very simple mapping to the other half of it. These are all valid reads. What would not be a valid read is if I were to ask for byte 1. And the reason for that is, well, if I ask for byte 1, I'm actually going to try and read like this or something, you know. I'm going to be looking at this part of the thing, and we cross a boundary here. So in order to do this, I actually have to execute 2 reads. RISC-V in the manual, or in the specification rather, it actually says that like reading across the boundary is fine. There's no problem with it. But what it does stipulate is that it doesn't have to be like implemented in hardware. It can be implemented so that if the hardware detects that you've done an unaligned read or a write, that that it can kick it up to software, and like with an interrupt, and software can handle it, which is really, really slow. But I guess it's an easier way of handling it. And for now, what I'm just saying in the what I'm going to say is that if you try and do an unaligned read or write in the emulator, that I'm just going to disallow it for now, because I think it will simplify things. So to check that, I'm going to do this thing, right? Because to make this clear, the way you can tell, right, if this is aligned, is you can see that there's a pattern to the way that this is legal, and that is that in all of these addresses, if you looked at it in binary, the last 2 bits would always be 0. So 4, the last 2 bits are going to be 0, 8, the last 2 bits are going to be 0, C, the last 2 bits are going to be 0. So if at any point you had like 2 bits that weren't 0 in the like the lowest positions of the number, then you would have an unaligned read. So it's really easy to check. So we can just say if address, and then we end off those like least significant 2 bits. If that is not 0, then we know we've got an unaligned access. Not 0, then just for now, just throw a new error. Unaligned read from address. And we'll do like a hex address, and I'm just going to make a util file because I'm going to use this function multiple times. util.ts. So export const to hex string. It's going to take an n, which is a number, and we're just going to say n.toString 16, which is going to convert it to like a 16-bit string, and then we can use pad start to say it needs to be 8 characters long, and like pad the start up and with zeros up until 8. So that would just give us like a nice hexadecimal number. And I'll also do this, right? The length is 8, so I'm going to parameterize this. So if we wanted to show smaller numbers for some reason, we could do that. I guess while I'm here, what I also might do is make a binary string version. And in this case, we want 32, because we're going to be dealing with like 32-bit numbers most of the time. So what we want to do is to say that if we put a 32-bit number in, we want to convert it to binary and just pad all the bits out. Cool, that will work for now. So we're bringing this to hex string thing, and we'll just throw an error that way. Okay, so what we're saying is that we've checked for unaligned. Well, we've checked for unaligned reads here, so we don't need to worry about it. The only thing we need to do is to divide the address by 4, which incidentally, and this all comes back to the same thing. The dividing by 4 is the alignment thing. So you can see that just if you shift off these 2 bits, that is a divide by 4, and shifting is just a division, right, by powers of 2. So shifting off 2 bits of this thing is gonna work like that. So what I want to do first is I want to get rid of that that 1 in the beginning. So I want to take off so I want to say we're going to read from address, and we're going to ignore not multiplied. We're going to ignore the first number because that's a selector. Then we're going to select everything else. 1, 2, 3, 4, 1, 2, 3, 4, yeah. And then the result of that, we'll shift that down by 2 bits. And I hope you see why I'm doing this, because this is now like a very hardware way of doing this. Like this is how we can do stuff in hardware, right? We're using ands, and we're using shifts, and we're using ands, and this is like an easy way for us to decode addresses. Like we can actually even do it simpler than this in hardware, but this is the way. In the end, if we end up reading from something that isn't legit, I'm just going to return. Is that going to be a good idea to do that? Yeah, for now I'm just going to, actually, you know what, just get back 0. Okay. And then we're going to want to return that. And we can do pretty much the same thing for the RAM. Okay. Can I select the right thing? RAM. Yeah, that's it. That should work exactly the same. And the these modules, the RAM itself has the 4 megabytes, and it's going to deal with wrapping around the address space within itself. So we're delegating responsibility of alignment to the system interface, and we're delegating responsibility of like checking the right size of stuff to the device itself. So whatever, we might not do that in hardware, but we'll see. I'm just going to copy paste this into the write method because it's pretty much exactly the same, except that is an unaligned read, it's an unaligned write, and we might want to print the value we tried as well. So value equals to hex string value. And yeah, so we're, instead of doing reads, we're doing writes, and then we need to give the value. And yeah, whatever, I'm just going to take that out because you can't write to ROM, so we're not we're not even going to call that method. It's a waste of time. This is going to be return RAM write the value. Cool, that's it for now. That is the whole interface. Oh, we're an hour in, so we've gone on. It's taken a little while to get to this point. I should have predicted we weren't going to get to instruction execution at this point. However, ROM. So let's make a new program ROM. Did I call it program ROM, or did I just call it? I call it ROM device. That was it. That, and we're going to want to have a RAM device as well. We need to find that. I really love TypeScript. I mean, I'm just I know this is the channel with low-level JavaScript, but TypeScript is just such a nice like addition to JavaScript. Like the type stuff is really useful, and I mean, it's hugely useful. But what I really love is like how much it allows for editor integration. Like you can just like do module imports and like auto fixes and refactorings in a way more effective way than you can in JavaScript. So I like it for that reason, mostly that editor integration becomes like so much nicer to use. But yeah, it's also really nice if you're working on the project, maybe a legacy project or something like that. And well, this is more like when you're thinking in hindsight to your legacy projects, and you think, oh, how hard it was to understand how data moved through an application. You really kind of don't get that with TypeScript. Well, you do. You do get it, but you have a way forward. You know, you can like click through the types. And you can go down the rabbit hole, but like if you don't have that, then you just need to do real archaeological digs on that. Okay, so the system interface, I'm just going to call it the bus here because it's sort of like that is what it is, and it's a little bit easier to pass a 3-letter word around than a word like system interface. So RAM or ROM. Plugged in, All right, so that's kind of that. Maybe we should check to make sure this works the way we think it does. So let's just make a RISC-V new RVI32 system. Let's load something into ROM and I guess into RAM as well. So first let's load something into ROM. So rv.rom.load new UN32 array, and let's put some recognizable numbers in there. Easy recognizable numbers are like 1, 2, 3, but maybe something like OX dead beef, OX code cafe. So we've got 2 things in there. Yeah, and then let's just console log 2 hex string rv.bus.read, and we're going to read from address. So this one is going to be at 0x1110, and then this one, because of alignment, is going to be at So let's check that. So we're going to read that. We're going to read 4, and let's read something unaligned just to see what happens there as well. So TS no, I'm probably going to see that I did something stupid here. Down. All right, we've got an. Okay, great. Dead beef, code cafe, unaligned read from address. That seems to work perfectly. Okay, so ROM, I don't really care about anymore. Let's write to the RAM and make sure that that works. So we should be able to write to something like address 20000000, and we can write, let's write something different in there. Let's actually just write the number 01, 02, 03, 04, and let's write to here. And actually what I should try is writing to something that's outside the 4 megabyte range as well, and just seeing if we wrap back around. So let's do this first. What I might do is also introspect the RAM a bit, just to make sure that because reading it back, well, I mean, there's no way this could go wrong at the moment, but so let's just try that first. Do we read back the right value? I read 0, so that actually didn't work. Have I put too many things down? 1, 2, 3, 4. 1, 2, 3, 4. All right. Let's go a little bit more hardcore and use the debugger. So I've already pulled in a VS Code thing that allows me to do TypeScript debugging. It's really simple. If you Google for it, you'll find it, but I can share it if someone needs. Now I'm doing TS test. This is something that I share in a bunch of projects, so I have it for mocker tests as well as just general debugging. Okay, so we'll dive in here. So we're doing a write, so we get past the unaligned part. And does the address map to RAM? Well, it does, so that's great. So here we're going to take the address, we're going to isolate the part we care about, chop off the unaligned part, and we're going to write that value in. So I'm actually going to jump right in here, and then, oh, okay, that is then the problem, right? That we don't actually need to do this. No, I'm wondering. I'm now trying to. The address is in terms of bytes, and the RAM size is also in terms of bytes. So I'm wondering, do I need to divide by 4? I don't think I do need to divide by 4 in these things. Like, this is. Because yeah, it's a bit late here, and I'm wondering if I've done this correctly. I'm also realizing that I haven't plugged my charger in, so it's maybe a good time to do that so I don't lose power. Won't be going for too much longer, actually. This was a bit ambitious to try to get this much done, but I'm looking forward to keep going on this. So anyway, what do we end up computing here as the final address? Let's just see that. RAM size is not defined. Well, okay, it is, but you can't see it for some reason. So I'm going to plug that in there. I'm just going to take away the multiply by 4 because we get the same thing in the end. We should just be writing to address 0, right? Because address is just 0. So we shouldn't end up with anything fancy here. So I guess then it's somehow we're getting something different in the read. Like so that means the RAM, this dot RAM. Yeah, I mean it's in there. All right, so we then do this. We do end up reading again. Address is still 0, so yeah, we should read that number back, right? Because you know, we still have it there. We actually do return that. Oh, that's so stupid. That's why you throw an error if you don't have something in your address space, because then you see that you made a stupid mistake. So actually it looks then like that probably works properly. Just run it again to make sure. Cool. And let's check this wraparound situation. So what we had was 1024 times 1024 times 4 gives us that. 16. And of course, like -1 gives us the 3FF. So if I chuck that, well, that's just if we write to without the -1, that's going to be writing to the. This is the first like wraparound value, right? Where do I need to shift this down to? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this should be writing to 0. So if we write this in here and we read this out here, we should read the same number because of this wraparound. Great, cool. So that all works. Nice. Yeah. So I think going any longer is going to be. Yeah, we're not going to be able to get into the pipeline properly. So that is, we're not going to actually be able to. You know what? Actually, we've got this part. What I want to do is just to lay the foundation of like how the pipeline is going to look. So I'm not going to write all of the pipeline stages or wire them together, but I do just want to like kind of draw out the interface, like sketch it out. Make a folder called pipeline. And I guess I'll have an index in here. No, you know what? I'm not going to call it index. I'm going to call it pipeline stage. There's not really an index for this. Unless I export all of the stages. So we're going to export an abstract class. That maybe sounds like all abstract class means here we're not doing anything like crazy OOP or something. Abstract class just means that like you can't instantiate this class. You need to extend it and implement the methods. That's it. Because each class is going to have to implement some stuff, and it's going to be specific per class. So I think this is going to make sense. Is this going to make sense? I guess. I don't know. We'll see. Pipeline stage. So the idea here, right, if we go back to this diagram quickly, so the idea is that a pipeline stage is going to have some stuff coming in and some stuff going out, and it's going to have some communication mechanisms between this channel, this stage and the next stage, and potentially more stages down the road. But in this very simple model, it's not. So like we need some way of communicating like, hey, we're ready to send data. I mean, we might find that some of this communication is not needed, but this is generally a useful interface when you have multiple modules that can take asynchronous amounts of time to get to their results, and they need to communicate and hold values until the next stage is ready. So what you do is basically each module just deals with its own stuff. It takes its inputs, it computes new stuff, and then like if it's ready, it will send them out. So one stage can be ready to send some stuff, but the next stage is actually not ready to receive it. So you have these two stages, one saying it's ready to send, one saying it's ready to receive. And the instruction fetch, if it's ready to send and the decode stage is not yet ready to receive, then it's fine, because it just looks at that signal and says, well, I've got all my values, I'll just hold on to them until the decode is ready. And so in that case, it's fixed in position. It's not going to move forward until it's been able to pass its value on. So as soon as ready to receive goes, it can say, hey, ready to receive has like gone. You can imagine these are electrical signals, right? So they sort of go high and go low to indicate that, like, you can say low means false and high means true. And so if send ready is high, receive ready is high on the same clock cycle, then they're going to be like, you can assume that on the next clock cycle they can start doing different kinds of work. And here, for instance, this is passing forward the instruction value. So we need this is the specific stuff from each stage, and these are always going to be the same. So we need to implement a function, a method that's going to communicate this stuff. So we're going to have a couple of things. We're going to have ready to send, right? Which is going to return, it's going to be abstract, right? We're going to expect that the class sends it, and it's going to just return Boolean. We need to be able to say we're ready to receive. So ready to receive, also a Boolean. And then we're going to have a couple of internal things as well. So for example, like when stuff comes into a stage, you have to grab that stuff and like put it in an internal register. So like hardware wise, you need to like latch it into an internal register, and then you hold on to it until you're ready. And then and because this is all going to be sequential in an actual like emulation, like we can only run one module at a time, right? Even like disregard promises or anything like that. It's like that's kind of unimportant. Like in electronics, like and in an FPGA, all this stuff is going to be running at the same time. So it's like the clock is going to be like the drum that stuff leads to. So like when the clock goes high, everything's going to start like doing its stuff, but like it's all going to be running at the same time. Whereas here it's not. Like, so what we need to do is we need to like have one stage where like we consider everything to be running on a clock, and like when we say the clock goes high, the module is going to compute its internal stuff, but because other modules are going to be like calling our methods for communication, like what we don't want to do is like change values that affect those inside like our computation method, if that makes sense. So what we want to do is separate the idea of like computing the stuff that's going wrong and then like committing it for the next clock cycle around. So I hope that's clear. I'm not sure if it is. I'm going to call compute is such a abstract name here. Yeah, I think I'm going to call it. I think I'm just going to call like one compute. Yeah, I'm going to call it compute. It's going to do void, and then we're going to have another method called latch next. that is going to be, and the idea here, right, is that when we implement this method, we'll have something like this, right? We can imagine that, let's implement this class quickly. So instruction fetch extends pipeline stage. We can imagine that we need to implement all of these methods, which is, I'm just going to ignore these two for now. So we need compute and we need latch next. Right, so you can imagine, right, that we're going to get some information out. So I'm going to have some variables in here, like the instruction is going to come in somehow, or we're going to fetch it. And we're going to do some stuff. We're going to put in some registers, and those registers might be like, the values that we compute here might be looked at by other stages of the pipeline. So I'm going to say that I have like a value A, and A is going to be looked at by the pipeline somewhere. It's going to be a number, but then I'm going to have, well, we'll expose an interface for it. So there'll be private variable, private, and then we'll have something called A next. And in compute, we're only going to deal with A next. Like, we'll have something here like get A, and here we'll you can imagine that the way the next stage gets A is by calling this method, right? So what we're going to do is we're going to work with A next here, right? So A next, some complicated stuff, whatever, we give it a value here. And what we want to do is we want to execute the compute method for every stage. And then when we've executed compute for every stage, we'll do this. And so what we're saying is that our values that can be seen by the other stages of the pipeline are only going to be valid on the next clock cycle. I really hope that makes some sense. It is quite important to get this right because, like, you know, if we're building an emulator for a game console that had a RISC-V processor, like, we wouldn't actually need to implement a pipeline like this. It's not really necessary. You don't need to go down to this level when you're actually implementing a CPU or emulating a CPU. But I want to do it here because I want to use this as the testing ground, right? So this is quite important to get right. All the internal values that we compute, we kind of don't want to make them visible to the outside world until the next clock cycle, because that's how it works in hardware. Like, it won't be like visible on an outgoing register until the next clock cycle. So yeah, so that's how it's going to work actually. So we're going to say that we need to implement these 4 methods at a minimum. And then let's just not implement, but just lay down instruction fetch. Export class, instruction fetch, extends. It's going to extend the pipeline stage. And we're going to have, in this one, some really concrete stuff, right? We're going to have an instruction register. I'm thinking it might be useful to build the concept of a register. So like a class that has a class that internally keeps track. JavaScript has some really specific things about how it deals with 32-bit, well, how it deals with numbers and when you use binary operations on them. Like, it will convert your number, no matter how big it is or whatever, it converts it to a 32-bit signed integer, which means if you can see this quite easily in Node, right? If I ff have this big number here, right? And that's fine. But if I was to just, like, what can I do that will, like, have no effect on this? If I OR this with 1, you can see that all of a sudden that turns into -1. And that is because the 2's complement, like in 2's complement, as in when you interpret this as a signed number, FF, 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 FF is -1. And so, yeah, it's a bit annoying when you're going to do these operations, because we have a 32-bit CPU here. We're going to have numbers that, like, this is going to happen anytime you have a number that's bigger than that's bigger than or equal to this this number, you know, because this number is the 1, 2, 3, 4. 1, yeah, because this is the very, very first number that's like part of 2's complement. If you're talking about, you know, counting up in terms of like 2's complement representation, it's the smallest number you can represent. So yeah, but of course it's just this in relative. So anytime we're dealing with a number bigger than this, and that will happen, right? Because instructions get encoded using like this format, and so like you just got a value up here that's actually just 12 bits, right? But like if that value happens to start with a number that's too big, it's gonna cause JavaScript to do weird stuff. So it's probably worth building a register class. Do I do that now? It's like I'm tangenting myself multiple times here. All right, register 32 TS. It shouldn't take too much to do this. Export class register 32. We won't use this everywhere, but it will be useful to use it in some places. We're going to have a private underscore value, which is going to start at 0. Yeah, we'll say that it starts at 0. Well, actually, we'll just say that it's a number because we're going to need to assign to it in the constructor. We're going to have a constructor where we take a start value, and then we'll just assign this value to value. And here I'm actually just going to assign this to 0 by default. Because a lot of the time you're just going to want to do that. And then what we'll do is we'll have a getter for get value. Then we'll just return this underscore value. And then a setter for value, so that I'm just going to call this one v. It's not really the best. We're going to have v. I wonder if TypeScript should know that we don't need to. No, of course it doesn't, because it doesn't know it's linked to the other one. So what we want to do here is we want to assign to this value here. So, but we can just check, right? If the value that we've been given here, after JavaScript has done stuff to it, it's going to end up being a negative number. So if v is less than 0, what we want to do is say this underscore value. We need to turn this back into a number that we can deal with all the bits. And the way you do that is you take negative v will turn it back into a positive number. Then we flip the bits of that and we add 1. And for the sake of not allowing numbers bigger than the 32 bits that we allow, because you actually can construct larger numbers than that, we'll end it off with FF. And otherwise, we'll say this value is just equal to v, right? Because otherwise it's fine. This is like sort of like already enough to take care of like most of the annoying stuff. So this can be a new register 32, starting at 0, and we need to import that. And then we'll have instruction next, right? Because we need to have a next version of that. And then we need to implement our 2 methods, so ready to send. have those be true for now. And then we have our compute. Have I misspelled that? I'm so bad at spelling that I would need to actually Google if I spelled receive right here. English is a really stupid language. Okay, so we're going to have compute, and we're going to have match next. So what we would want to do here, right, is we would we also need to have a constructor where we're going to take in this export an interface, which is going to be instruction fetch params, and one of those is going to be the bus, which is the system interface, and then we'll keep a bus, which is a system interface. And actually in this, like, there's a reason that I will do this, because I don't want to like copy all the types from here to here all the time, so we can just do this instead, and now this actually refers to that system interface type. Here we're going to take our params, which is going to be instruction fetch params, and we can say this.bus equals bus, params.bus. Cool. We need to call super because of the rules. So here what we would have is we also need to have like a signal that tells us whether we're going to stall or not. And stalling is just means basically like take no effect, like do nothing, keep all of your internal values in this stage. So should stall, and what that's going to be is just a function that returns a boolean. We're going to pass that in. Should stall, and we'll so we can say if not this dot should store, so in other words, like, are we allowed to compute? Like, are we allowed to like figure out our next value? If we're not stalling, then like there are some more conditions that we need to deal with here, but I'm just going to do this for now to illustrate the point. So this dot instruction is going to be oh, we need another register actually, and that is going to be program counter. And program counter will start at memory map dot program rom start. And we're also going to have private PC next, right? We want to do this with all of the register, even though I don't think we're going to expose the program counter. I'm still going to do this next thing. So this is how we're going to do it, right? This dot instruction next will be this dot bus dot read this dot program counter dot value. Cool. Number is not assignable to register 32. True. We need to assign to the value. And then we can say that this.pc.value is going to plus equal 4, because we're reading 32-bit integers, and by now I hope you see that there are 4 bytes per 32-bit integer, and so we can only read aligned. So we need to move those 4 bytes along. And it's not pc.value here, it's pc.nextValue. And when we latch that, we're going to say this.instruction.value equals this.instructionNext.value, and this.pc.value equals this.pcNext.value. And what will happen is that when the CPU runs these pipeline stages is going to run all of the compute stages first, and then all of the latches afterwards. And then that will make sure that we're going to expose this instruction, right? So I'm going to also just implement get instruction. I'm going to call it get instruction out because pipeline stage is eventually going to, like the first stage is only going to put out the instruction, but each subsequent stage, it needs to both take stuff to pass along to the next stages, even if it doesn't need it. If the next stage needs it, we need to pass it along the chain. So what happens is each stage is going to have a bit more information than the last one. So you're going to have stuff coming in and stuff going out. And I think it might be a good naming convention to have stuff that comes in, like be labeled with in, and stuff that goes out be labeled with out. We'll see how that works. And here you can see we're just returning instruction, right? So yeah, so anything that calls is only going to get like the, even if this stage runs first and then another stage runs afterwards and it needs to compute, it's not going to see this value. And that's good, right? Because that's how it will be in the hardware. It shouldn't, like, stuff doesn't run sequentially in hardware, so we wouldn't expect that this value would be propagated to the next stage somehow. It's going to see this one. So that's the whole thing. Kind of hoped we'd get further, but we've been going for an hour and a half, and I don't see how we possibly could have now. That's always the way. I hope you've enjoyed this. And I hope you're excited in some way as well about going on this journey with me. Feel free to leave some comments. Feel free to subscribe if you're not subscribed, and yeah, just let me know what you think or if you spot a mistake. And that's it. Thank you for watching. I'll see you next time.